Recently in one of my Monday night live streams, which I'm doing every Monday night at 5 Pacific, I talked about how to decide between whether you're going to use u-substitution or integration by parts, which I then made its own video about, and that was my last video that I came out with. But I wanted to keep building on that because in that video I talked about a couple different examples, and I want to show you how to actually integrate these examples. So today I'm going to be showing you the easy steps that you can go through and the thought process that I go through when I'm doing an integration by u-substitution problem, so that you can apply this on your own and solve integration by substitution problems a lot easier on your own. If that sounds good to you, be sure to stick around to the end. And if you do, these types of problems should be a lot easier for you. Anyway, let's go ahead and jump on into the example. Okay, so basically at this point we've decided u-substitution is probably going to be easier, or maybe not easier, but more likely to work, I should say, because there isn't going to be an easy way to break down this function into the integration by parts formula. So getting into these options here, like I said, really these four possible options for what we could call our u. So based on these four, like I said, one of these first two is probably going to be our better bet, because the derivative, if we were to make our u either of these other two things, the derivative of these two things is not somewhere else in our function. So as a result, we probably want to try one of these two. Now, the thing you want to keep in mind, if you are in a situation like this, and this does actually happen fairly often, where you have two or more potential options for choosing your u, where the derivative of those two things is exactly the same. So like the derivative of x squared is 2x, the derivative of x squared plus 1 is also 2x. Usually, choosing the u to be the bigger term is going to help simplify your integral more, and therefore making it the better option. So let's go ahead and say that our u is going to be x squared plus 1. And the reason is, you can see that if we make our u x squared plus 1, and then when we think about putting that into our integral, our entire denominator, or everything within the parentheses here, I'm sorry, not our entire denominator, but everything within the parentheses is going to change to a u. So we're still going to have our x here, and now we're going to have u squared on the denominator, which is, quite a bit more simple than if we were to, use this other option for u of u equals x squared. We would end up with the integral of x over u plus 1 all squared, which, depending on what we had on our numerator, maybe that would be better, but generally the more stuff you can kind of substitute out, the better off you're going to be. So now that we have decided that our u is going to be this, we also need to figure out what is du. Well, du is just going to be the derivative of whatever your u is. So in this case, x squared plus 1, we can take the derivative using the power rule. The derivative of x squared is going to be 2x. We just bring our power down in front, lower the power by 1. X to the 1 is just x. And then the derivative of a constant is 0. So we're just going to get 2x dx. Remember, when you're doing u substitution, when you take this du, you always want to add on the dx over here as well. So now what we can do is we can take this and we can solve it for dx, which just means divide 2x to the other side, giving us dx equals du over 2x. And the reason why we wanted to do that is now we can substitute this in for our dx here. So we're going to have x over u squared times du over 2x. And now, because of the fact that we chose our u so that u's derivative was also somewhere in the function, now this x is going to conveniently cancel with this x here. So now what we actually have is the integral of basically du over u squared, which is going to be quite a bit easier to actually find the integral, or the antiderivative of, than our original function. So let's go ahead and take that down here. We have the integral of du over u squared. Okay, now what we can kind of think about doing with this, let's just think about how we could rewrite this into a form that is going to be easier to integrate. Well, what you first want to keep in mind is du over u squared is the same as 1 over u squared du, which is a form that's a little easier to interpret, because what this is telling us is we're going to integrate this function right here with respect to u. The du is just kind of an indicator of what variable we're integrating with respect to. So now what we can also do is we can rewrite this. Instead of having it as a fraction, we can rewrite 1 over u squared as u to the negative second power. So now we don't have a fraction. And the reason why this is really nice is because now this is actually in a form where we can use the power rule to integrate, which is much better or much easier than just about any other integration method. So the power rule for integration says that we would keep our base the same. We would raise our power by 1 or add 1 to it. -2 plus 1 is -1. And then we would divide by our new power. Our new power is -1. So u divided by -1 is the same as u times -1, which is just -u. So -u to the -1, which we can then do the exact opposite thing of what we did right here and put this back into -1 over u. Because if you're moving things from the numerator to denominator or vice versa, you can just make their power negative of what it was and flip it over the fraction like that. So in this case, we made it negative to move it up to the numerator. In this case, we're making it from negative to positive to move it back down to the denominator. But we're not quite done yet, because remember, what we have at this point is a function that was the antiderivative of this function, which we had after substituting out for u. So basically what we have now is something that doesn't actually make any sense in the context of the original problem, because the original problem gave us a function of x and said to find the antiderivative. What we have now is a function of u. So now what we need to do is make this substitution back to put it in terms of x. So we're going to go back to our function, replace u with x squared plus 1, which would give us -1 over x squared plus 1. Actually, wait a minute. I missed something. Yes, I did. Okay. Sorry, go back a little bit. I'm missing my constant. I forgot to carry that through. So all the way back up to this step here. Sorry about that mistake. We had here du over 2x. The x canceled with this x. We still had a 2 on our denominator. So we should have had a 2 down here with our u squared, which we can pull out of our fraction or pull out of our integral because it's a constant. So we can pull out a constant 1/2 out in front of this integral, and that would basically just carry all the way through. So we'd have 1/2 there, -1/2 u to the -1, which would put a 2 there, which would put a 2 here. So our antiderivative, this is the correct one now, sorry about that, is actually -1 over 2 times x squared plus 1 in parentheses. Well, I hope you found this video helpful. If you did, please be sure to hit that like button down below. And if you want to check out my integral calculus cheat sheet or my calculus 2 study guide, there is a link down in the description or the pinned comment below where you can learn more about that and get your very own copy of that immediately. If you want to keep this brain train rolling a bit and keep learning about u-substitution or other integration methods, I have made some other videos on all that stuff. Go ahead and click on one of those over there, and see you next time.